Right, chemistry. We're continuing our deep exploration into the structure of the atom, and this is called electron configuration. So electron configuration is a notation for the orbitals and subshells that the electrons of an element occupy. The order that electrons fill energy levels can be determined by reading the periodic table like a book, from left to right and top to bottom. This produces the following ordering of the subshells. And go ahead and have your periodic table in front of you as you watch this lesson. So the first row we have the 1s subshell. The second row we have the 2s subshell, and then over on the right side the 2p. That would take you from boron through neon. Then we have the 3s, sodium, magnesium. Then the 3p, which goes aluminum through argon. Then the 4s, which would be potassium and calcium. And then you have the first row of transition metals, which would be the 3D. And that would take you from scandium through zinc. And then the 4P, which is gallium through krypton, and on down. So it's simply left to right, top to bottom, just like you read a book. The energy levels are ordered in a bottom to top structure called Aufbau, which is German, that means build up. Okay, so now you see, rather than drawing circular orbitals, this is the kind of the more sophisticated and a more detailed way of showing orbitals and subshells. Okay, so we're going to show where each of these is on the periodic table. And so the first one, the 1s, is the first row. That's hydrogen and helium. The second is the 2s, and that includes lithium and beryllium. Then we go over to the 2p, and that's boron through neon. And you notice it's broken into three sections. So those separate parts there, Px, Py, Pz, we're going to refer to those as sections. Then we go to the 3s, that's sodium and magnesium. Next is 3p, 3px, 3py, 3pz. Next is 4s. We're down to potassium and calcium. And then the transition metals come in, and those are the 3D subshells, and there's 10 electrons that can fit in those subshells, 2 in each of those sections. Next we go across and we have the 4P, there's 3 sections there, and then the 5S, and then we have the 4D right there, and then the 5P, and then the 6S down there, and now although one element in the 5D appears first, you really have the 4F after that, and that's this up here. That's the lanthanide series, and there are 7 sections there. Each can hold 2 electrons for a total of 14 electrons. Okay, now when you have 3 of these sections that are really the same energy level, they're just 3 separate parts, that's referred to as degenerate energy levels. It sounds like a bad word, degenerate, but it's not. It just means the same. In science, degenerate just means the same. Okay, 3 rules determine how electrons are placed in the Aufbau structure. The first one is the Aufbau. You always go from the lower energy level first and build upward. So the electrons are going to fill the lowest ones and move upward. Next, Hund's rule. Electrons of the same spin, that is up and down arrows, are placed in degenerate subshells to spread out before those with opposite spins. So this is very much like what we did when we drew the atom with circular orbitals, and the way that you spread the electrons around an orbital before you started pairing them up. That's what this is. What spin means is, it means that if two electrons are negatively charged, so they repel each other. But if they have opposite spins, that means they're less repulsive of each other. They can kind of stay together or near each other if they have opposite spin. You don't need to really understand the concept of spin any more than that. The Pauli exclusion principle, 2 electrons can have the same 4 quantum numbers. We don't learn about quantum numbers in this class, and it's not tested on the AP. So now we're going to see how the electrons build up. Okay, there you see down on the very bottom left, 1s, that's hydrogen, and then an opposite spin is helium. The 2s, this would be lithium, and then beryllium. They have to have up arrow, down arrow to do that. Next we go, and we'll see Hund's rule in the 2p. You have an up arrow, and then an up arrow, and then an up arrow. They want to spread out first. Then they start pairing up, down arrow, down arrow, down arrow. Now we go to the 3s, up arrow, down arrow, 3p, up arrow, up arrow, up arrow, down, 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 4s, up, down. Now we're over to the 3D. We're in the first row of transition metals. Okay, this is scandium. And then we go across, up arrows all the way across, and then we start pairing with down arrows until we get to zinc at the end of the transition metals third row, the 3D transition metals. Okay, now we got P's, 4 P's, up, 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 down, 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 and then 5S, up, down, and then the 4D. Okay, so we're starting with yttrium, and we're going to end up over here with cadmium, right there, right there. Okay, now we're at the 5P, up, 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 down, down, down. Now 6S, and then you get into the first row of F orbitals. Those are the lanthanide series at the bottom of the periodic table, and that's going to be, there's 14 electrons. There's seven sections, but 14 electrons. Each section can hold 2 electrons, and that's as far as I'm going to go with that. Okay? All right, now we're going to learn about electron configuration. The AP exam would not ask you to draw what you just saw, but they will ask you to be able to state or recognize or read an electron configuration. So here we go. So this is the first electron in the 1s orbital. So the electron configuration notation is 1s1. So 1 means the first orbital, the S means the S subshell, and the superscripted 1 means 1 electron. It's not an exponent, it's not mathematical, it just means 1 electron. Then you have a second electron, that would be helium, and that's going to be 1s2. So it's in the 1s subshell, and there's 2 electrons. Now we're going to go up to the 2s, and by the way, that gives you the electron configuration of helium. Now we're going to go up to the 2s, and now you got 1s2, 2s1. So you have to say both of those things. You can't just say 2s1. Now we're going to put a second electron there, and now you have 1s2, 2s2. Now we're up to the p subshell, and you have a 2p1. Then you add a second, and it's 2p2. Then you add a third, and it's 2p3. Notice you don't write px, py, pz. It's just p. They're all in the p subshell. Now you're going to add the fourth, 2p4, fifth, 2p5, and sixth, 2p6. When you're at the end of a p subshell, with the exception of the 1s, anytime you're at the end of a p subshell, you're at a noble gas. And so this would be the electron configuration of neon. So we're going to go ahead and put neon there. All right, now we go up to the 3s. 3s1, 3s2, and now we're up to 3p, 3p1, 3p2, 3p3, 3p4, 5, and 6. And now we're at the end of another p subshell. That's going to be argon. Now 4s, we'll continue through this a little faster. 4s1, 4s2, and now you got the 3d. All right, so you're going to have quite a few of those. And 3D, 4, 5, 6, all the way up to 3D10, like that, okay? And that's going to be, that's not a noble gas. It's at the end of the D subshell. That's going to be zinc. It's at the end of a transition metal. Now you go up to the 4P, okay? And that's starting with gallium. And we go through those, all the 4Ps. And we're at the end of another P subshell. So that's going to give us the next noble gas, which is going to be krypton, and you see the notation down there. Okay, 5s, we'll push through those, and then you got to go to the 4d, okay, and now we're at the 5p, and we do those, and at the end of the 5p, we have xenon, the noble gas xenon. You see that down there at the electron configuration, okay? And then 6s, and we'll just kind of plow through those, and you're going to end up with 14 in the 4f subshell. All right, so that's what that notation would look like down at the bottom if you went all the way up to 4F14. A lot of writing to do. But you can do the condensed electron notation simply by writing xenon, the noble gas in the previous row, So that would be xenon, and then write the rest of what you have there. So the xenon takes you all the way through 5p6, and then you still have the 6s2 and the 4f14 after that. So you go ahead and write it, and you can see that the condensed electron notation is much shorter. Okay, so now we're going to do some elements here. So write the electron configuration and condensed electron configuration for potassium. So you see it's the first element in the fourth row. So we're just going to kind of fast forward up there like this. You can read those as you see them come up. Okay, now we're at a noble gas. Okay, another noble gas right now. Okay, and then 4s1 is right there. So that would be the electron configuration for potassium. Now the condensed electron configuration, there's the 4s1. The condensed would be this. You simply take everything you see in the bracket, call it argon, and then add the 4s1 after that. So it would be Ar, argon in the square brackets, 4s1. All right, now we're going to look at the potassium ion. That's potassium forms a 1+ ion. You know that by looking at the periodic table. So we're going to fast forward up the potassium again. You can see it's the same thing you saw on the last slide. Okay, and there it is, 4s1. All right, so now it's potassium 1+. So that means it's going to lose that electron in the 4s. That's going to be ionized. So you're going to go ahead and just take that off. And there it is. Potassium has the electron configuration of the noble gas argon. We know that when atoms ionize, they want to be like the nearest noble gas. Okay, so that's the potassium ion. Okay, now we're going to get into one of the quirks of this. It's a little bit unusual. It's one of the exceptions you got to learn. Okay, and they will ask you this on the AP exam, because they know if you know this exception that you'll know how to do any of these. Okay, so here we go. We're going to do chromium. So you find it on your periodic table. It's the fourth element in the 3D row. It's Cr. So I'm going to fast forward up there. Okay, and here we go. It's the fourth element over 1, 2, 3, 4. That would be chromium. That's the way you would do this. However, read what's up on the top. Filled and half-filled subshells are more stable than other configurations. This results in some exceptions to the order we have just seen in the 3D subshell. So watch what happens. Down at the bottom it says, since chromium will be more stable if it has a half-filled 4s and a half-filled 3D orbital, the 3D orbital will borrow an electron from the 4s. So watch what happens on the diagram. You take that electron in the 4s. Okay, and we're going to put that electron up there. And so now the 4s is half filled, which is still stable, but the 3D is now half filled. And so it's more stable than it was before. And this is the electron configuration. So what you're going to end up with is Ar 4s1 3d5. Okay, let's do one more. How about copper? Go ahead and see if you can figure this one out. It's the 9th element in the 3D subshell, right next to zinc. Okay. All right, so let's look at it. We're going to fast forward up to that. Okay, here we're in the 3D, and now here we go, and there. That would be copper. It would have 9 electrons in the 3D subshell, but it's going to do the same thing as we did with chromium. It's going to borrow the 4s, it's going to take it away, and now it's going to put it up in the 3D. So now you have a half-filled 4s, which is still stable, but now you have a filled 3D, which is more stable than if it only had 9 electrons. Okay, so that takes care of how we do electron configuration.